Denoising Monte Carlo renderings via a multi-scale featured dual-residual GAN. Part 1. Introduction. Monte Carlo path tracing is a famous and effective way of physically based rendering. It generates photorealistic results at sufficient samples per pixel. It's convergent and unbiased, but it's also very time-consuming and very noisy at low SPP. This is because a surface point reflection energy is an integral over solid angles. Computers cannot handle solid angles, but a single direction instead. So we need to sample tremendous directions to simulate this process. Also, the path tracer could generate useful auxiliary images such as albedo, depth, and normal. Also, we can separate the rendering into two branches, specular and diffuse. Considering the huge time cost, instead of continuing sampling, we choose to fix the low SPP result via a neural network. Part 2. Network structure. As mentioned above, the auxiliary features are easy to get and is very helpful for the denoising task. At first, researchers simply concatenated the noisy colors and the auxiliary features as the network input. Then Xu and Wang shows that encoding noisy color and auxiliary features separately gives us better performance. They use a VGGNet as the auxiliary features encoder net, and they implement a module called Conditional Feature Modulation (CFM) to fuse the auxiliary feature and the main feature inside the denoiser. Their work also shows the improvement by implementing generative adversarial network. This is the overall figure of our network. Please notice that we use the two same structure networks to operate on diffuse and specular separately. A network will have a denoiser, an auxiliary buffer encoder in which we use the multi-scale convolution dense block, and a discriminator. The discriminator only affects the training. Such design is similar to Xu and Wang's work, but there are three main differences. We use residual-in-residual design in the denoiser. We introduce dual-residual connection to the denoiser. And we use multi-scale design in the auxiliary buffer encoder and the discriminator. Some methods make the network output multiple kernel filters and then use them to filter the noisy input. In our method, we make the network directly output the denoise result, which means the last convolution layer of our network has only 3 channels matching RGB. Let's take a look at the denoiser. Because we are building a very deep network, we want the features to flow between layers as much as possible. Therefore, our denoiser uses the residual-in-residual design, which means it has a long skip connection, several middle skip connections, and several short skip connections. Under the long skip connection, we stack 3 dual residual groups, shown as DRG. Each dual residual group receives the auxiliary feature from auxiliary buffer encoder. The ablation study shows that the residual-in-residual design can improve the network's performance. In a dual residual group, we can see a middle skip connection and 2 dual residual blocks. Inside a dual residual block, there is 2 residual units, shown as RU, and there is also a channel attention module, which help the network pay attention to the important features. Then we introduce dual-residual connections, shown as the blue lines and the red lines. The dual-residual connections have made improvements in noise removal, motion blur removal, object detection, etc., because it offers more path choice for the features. But our dual residual connection is a bit different from the original paper. The blue lines can be seen as the vanilla residual connections of the ResNet. And the red line will stride over a residual unit. Therefore, the first unit of a dual residual block doesn't take in red line. This is the inner structure of our residual unit, showing how the red lines and the blue lines transfer the features. Also, the residual leaving the dual residual group is the sum of the two residuals. The ablation study shows that the dual residual connections can improve our network performance. And inside our dual residual block, we use the conditional feature modulation to fuse the auxiliary features and the feature inside the denoiser. After the conditional feature modulation, we stack two convolution layers and a channel attention module. But we replace the first convolution layer with the spatial adaptive block and the third dual residual group. The spatial adaptive block has a deformable convolution layer. It takes in offset values generated by the offset block, in which we use 3 convolution layers and a spatial attention module. The deformable convolution can make the network adapt to different spatial changes and improve its flexibility. Removing SAB produces artifacts at the edge between low-frequency information and high-frequency information, and failed to restore reflected illumination. Our auxiliary features are generated by the multi-scale convolution dense block. It first stacks 3 convolution layers to extract shadow features. Then we use the convolution dense block, shown as CDB, and multi-scale feature fusion block, shown as MSFFB, to further extract deep features. The convolution dense blocks are designed in the well-known DenseNet style. The multi-scale feature fusion blocks uses the multi-scale design. We have 3 scales. In each scale, we have 2 convolution layers and a channel attention module. After the 3 scales, there is a selective feature fusion called SKFF to fuse the 3 scales. The multi-scale design can restore more information than single scale, and the SKFF can produce better results than simply concatenate the 3 scales. Our discriminator is designed in a patch GAN style, but we use a Laplacian filter to make the discriminator pay attention to the edge information. Therefore, it will prompt the generator to generate high-frequency details. Part 3. Evaluation. We use public Disney scenes. The noise-free images are rendered under 32,000 SPP by the tungsten renderer, and the noisy images are rendered under 32 SPP. All the images are cropped into 128 patches when training. We divided the input color by the albedo map, and then multiply the output by the albedo map. By doing so, the network won't damage the high-frequency detail in the textures. Also, We use log transform to compress the dynamic range of the input color. Our network has fewer parameters and less inference time. All the methods are trained using 32 images, but we also run the test on other SPPs. At each SPP, our method has the largest ratio of best denoising result. And it's perceivable that our method generated the best result. This is the jar scene rendered under 32 SPP. And this is the kitchen scene rendered under 4 SPP. And this is the coffee maker scene rendered under 16 SPP. And this is the glass of water scene rendered under 16 SPP. Part 4. Limitation. Due to the lack of diversity of the training data, our network cannot handle some special situations in the testing scene. For example, in the curly hair scene, it blurs some hair, making it look like a whole piece. And in the glass of water scene, it also blurs the cavities inside the ice cubes. Also, our training dataset doesn't contain any visual effects, such as motion blur and depth of field. We haven't run the test on those things yet, but we can expect that the current model can't handle them. However, this isn't really a bother in our task, because most visual effects are post-processing after the renderings. So we can denoise the rendering first. Then we implement motion blur or depth of field onto it, as long as we have saved the motion vectors and the depth into the G buffer. This is the end of my presentation. Thanks for your attention.